Hello friends, today we are going to start a series of lectures on mechanics. It is a branch of classical physics that deals with the particles that are moving or that are at rest. It can also be defined as a branch of science which deals with the motion and force of the particular particle or a system of particles. For example, as shown in this figure, if you toss a ball into the air without much spin on the ball, its motion is simple. It follows a parabolic path and the ball can be treated as a particle. If instead you flip a baseball bat into the air, its motion is more complicated. Because every part of the bat moves differently along paths of many different shapes, you cannot represent the bat as a particle. Instead, it is a system of particles, each of which follows its own path through the air. However, the bat has one special point, the center of mass, that does move in a simple parabolic path. The other parts of the bat move around the center of mass. In a system of particles, center of mass forms an important parameter. We define the center of mass of a system of particles such as a person on motorcycle in order to predict the possible motion of the system. The center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. In this section, we discuss how to determine where the center of mass of a system of particles is located. We start with a system of only a few particles and then we consider a system of great many particles as a solid body such as a baseball bat. System of particles. The figure shows two particles of mass m1 and m2 separated by distance d. We have arbitrarily chosen the origin of an x-axis to coincide with the particle of mass m1. We define the position of the center of mass of this two particle system to be x center of mass is equal to m2 upon m1 plus m2 into d. Suppose as an example that m2 is equal to 0, then there is only one particle of mass m1 and the center of mass must lie at the position of that particle. This equation then reduces to x center of mass is equal to 0. If m1 is equal to 0, there is again only one particle of mass m2 and we have, as we expect, x center of mass is equal to d. If m1 is equal to m2, the center of mass should be halfway between the two particles. The equation reduces to x center of mass is equal to half d as we expected. Finally, equation for center of mass tells us that if neither m1 nor m2 is 0, x center of mass can have only values that lie between 0 and d. That is, the center of mass must lie somewhere between the two particles. Now, this figure here shows a more generalized situation in which the coordinate system has been shifted leftward. The position of the center of mass is now defined as x center of mass is equal to m1 into x1 plus m2 into x2 over m1 plus m2. Note that if we put x1 is equal to 0, then x2 becomes d and equation B reduces to equation A. Note also that in spite of the shift of coordinate system, the center of mass is still the same distance from each particle. We can rewrite equation B as x center of mass is equal to m1 into x1 plus m2 into x2 over m, in which m is the total mass of the system. Here m is equal to m1 plus m2. We can extend this equation to a more general situation in which n particles are strung out along x axis. Then the total mass is m is equal to m1 plus m2, so on up to mn, and the location of the center of mass is given by this equation, where x center of mass is equal to the total mass, which is represented by m1 x1 plus m2 x2 plus m3 x3 and so on up to mn xn, divided by the total mass m. Or we can write this equation as 1 upon m sigma mi into xi. The subscript I is an index that takes on all integer values from 1 to n. Center of mass in 3 dimensions. If the particles are distributed in 3 dimensions, the center of mass must be identified by 3 coordinates. So, by extension of equation C, they are for x axis, x center of mass is equal to 1 upon m sigma mi into xi. For y axis, it is y center of mass is equal to 1 upon m sigma mi into yi. For z axis, it is z center of mass is equal to 1 upon m sigma mi into zi. Solid bodies. An ordinary object such as a baseball bat contains so many particles that we can best treat it as a continuous distribution of matter. The particles then become differential mass elements, that is dm, and the sum of center of mass in 3 dimensions becomes integrals, and the coordinates of the center of mass are defined as, for x axis, x center of mass is equal to 1 upon m into integral x dm. For y axis, it is y center of mass is equal to 1 upon m integral y dm, and for z axis, it is z center of mass is equal to 1 upon m into integral z dm. Here m is now the mass of the object. Evaluating these integrals for most common objects such as a radio set or a keyboard would be difficult, so here we consider only uniform objects. Such objects have uniform density or mass per unit volume, that is, the density rho is the same for any given element of an object as for the whole object. So, density rho can be defined as volume occupied by a mass element, that is dm, divided by the total volume of the object, that is dv. We can write this in equation form as rho is equal to dm upon dv and is equal to m upon v. Now, we can get the coordinates of center of mass of solid bodies in another form by substituting m upon v into dv for dm in coordinates equation of solid bodies. Therefore, center of mass for x axis, which was 1 upon m integral x dm, becomes 1 upon m integral x m upon v dv, and it again becomes 1 upon m into m upon v integral x dv. Here m and m cancel and we get x center of mass is equal to 1 upon v integral x dv. Similarly, center of mass for y axis becomes 1 upon v integral y dv, and for z axis it is z center of mass is equal to 1 upon v integral z dv. You can bypass one or more of these integrals if an object has a point, a line, or a plane of symmetry. The center of mass of such an object then lies at that point, on that line, or in that plane. For example, the center of mass of a uniform sphere which has a point of symmetry is at the center of the sphere, which is the point of symmetry. The center of mass of a uniform cone whose axis is a line of symmetry lies on the axis of the cone. The center of mass of a banana which has a plane of symmetry that splits it into two equal parts lies somewhere in the plane of symmetry. The center of mass of an object need not lie within the object. There is no dough at the center of mass of a donut and no iron at the center of mass of a horseshoe. Now, we shall solve a sample problem related with the center of mass. Figure here shows a uniform metal plate P of radius 2r, from which a disc of radius r has been removed in an assembly line. The disc is shown in figure B. Using the xy coordinate system, locate the center of mass of the remaining plate. To solve this, let us roughly locate the center of plate P by using symmetry. Note that the plate is symmetric about the x axis. Thus, center of mass of plate must be on the x axis. The plate with the disc removed is not symmetric about the y axis. However, because there is somewhat more mass on the right of the y axis, center of mass of the plate must be somewhat to the right of the axis. Thus, the location of center of mass of plate should be roughly as indicated in figure A. Our job here is to find the actual value of the location. Now we know that the plate P is an extended solid body. So, in principle, we can use the following equations to find the actual coordinates of the center of mass of plate P. Here we are simply looking for the xy coordinates of the center of mass because the plate is thin and uniform. If it had any appreciable thickness, we would just say that the center of mass is midway across the thickness. Still, even neglecting the width using these equations would be challenging because we would need a function for the shape of the plate with its hole, and then we would need to integrate the functions in 2 dimensions. So, what do? We got to find an easier solution. So, the easier way is in working with centers of mass. We can assume that the mass of a uniform object, as we have here, is concentrated in a particle at the object's center of mass. Thus, we can treat the object as a particle and avoid any two-dimensional integration. Therefore, first put the removed disk, call it disk S, back into the place as shown in figure C to form the original composite plate, which is called the plate C. Because of its circular symmetry, the center of mass, that is COM S for disk S, is at the center of S. Similarly, the center of mass COM C for composite plate C is at the center of C at the origin as shown. Now we have the following parameters: the plates, the center of masses, location of center of mass, and the mass. Assume that mass ms of disk S is concentrated in a particle at xs is equal to minus r, and mass mp is concentrated in a particle at xp as shown in figure D. Next, treat these two particles as a two particle system using equation B. So, we have equation B as m1 x1 plus m2 x2 upon m1 plus m2. We find their center of mass and get x s plus p is equal to ms into xs plus mp into xp over ms plus mp. Now note that the combination of disk S and plate P is composite plate C. Thus, the position x s plus p of COM S plus P must coincide with the position x c of COM C, which is at the origin. So, x s plus p is equal to x c and is equal to 0. Substituting this into equation S1 and solving for xp, we get xp is equal to minus xs into ms upon mp. We can relate these masses to the face area of S and P by noting that mass is equal to density into volume and is again equal to density into thickness into area. Then ms upon mp is equal to density S divided by density P into thickness S divided by thickness P into area S divided by area P. Because the plate is uniform, the densities and thicknesses are equal, we are left with ms upon mp is equal to area S over area P and is equal to area S divided by area C minus area S, and ms upon mp becomes equal to pi r square divided by pi into 2 r square minus pi r square and is equal to 1 by 3. Substituting this and x s is equal to minus r into equation S2, we have x p is equal to minus x s into ms upon mp. Therefore, x p becomes equal to 1 upon 3 r. So, friends, here we come to the end of our discussion and therefore, we sum up. In this lecture, we learned that the center of mass of a system of particles is the point that moves as though all the system's mass were concentrated there and all external forces were applied there. The center of mass of a system of n particles is defined to be the point where coordinates are given by these three equations. So, that is it for today. In the next lecture, we shall be discussing about Newton's second law for system of particles. Thank you very much.